In this two-part example, we'll solve a system of ODEs describing the dynamics of an epidemic spreading throughout a population. In the last video, we derived the coupled system of first-order ODEs by hand and lumped the ODEs into a 3x1 vector of ODEs. In this video, we'll implement the vector of ODEs in Matlab. Here I have a script with some parameters already typed out at the top. The A and R parameters are taken directly from the problem statement. We then have three initial conditions, S0, I0, and R0. According to the prompt, the city initially has 10,000 susceptible people and a single infectious person. This implies R0 equals 0 because in order to be recovered, you must first be infected, so there can't be any recovered people when the epidemic is first introduced to the city at t equals 0. Keep in mind that we need three initial conditions because we have three first-order ODEs. I also made a time vector going from 0 to 40 days in increments of 0.01 days. The problem doesn't explicitly tell us how long to simulate, but I played with the problem beforehand and found 40 days to be sufficiently long. The next part of the script includes a call to the function called epidemic, which is a custom function located at the bottom of the script here. The rest of this section just plots the outputs. This brings us to the epidemic function. I wrote a custom function to solve the system of ODEs. It takes 6 inputs, all of which are hopefully self-explanatory, and returns 3 outputs, which are the susceptible, infected, and recovered groups, respectively. In the last video, we expressed the system of coupled ODEs in terms of a 3x1 column vector, y. We said that the first element of y is s, the second element is I, and the third is r. If we differentiate y with respect to time, we get dy dt equals ds dt, di dt, and dr dt, which is just these right-hand side terms we derived from the population balance. Notice how s is just the first element of the y vector, so we substitute the s here with y of 1. I is the second element of the y vector, so we substitute this I with y of 2. In total, the negative ASI term becomes negative a times y of 1, which is s, times y of 2, which is I. We can make the same substitutions for the ASI minus RI and the RI terms down here. This allows us to express the entire system of ODEs in terms of our new single variable, y. We do this because we have to solve all three ODEs simultaneously since they're coupled. Let's write the anonymous function handle we'll input to ODE 45. Here we have the dy dt variable. It looks the same as any ODE we've done in the past, except now it has 3 rows in 1 column because we said the y vector is a 3x1 column vector. We then called the ODE 45 function as normal with the slight tweak that we provide all 3 initial conditions in a vector. When you supply the initial conditions, you have to give them in the order in which you define the vector of ODEs. For example, we said ds dt is the first element of the dy dt vector, so we have to give s0 first. If we said dr dt was the second element of dy dt instead of di dt, we would have to provide r0 and then I0. I'm ignoring the time output from ODE 45 because we supply our own time vector. I'm going to add a breakpoint and run the code just to show you what happens. As the name implies, this is just a dummy variable I'm using so I can place a breakpoint. In the workspace, we now see the y variable, which has 4001 rows and 3 columns. It has 4001 rows because our t vector has 4001 elements. It has 3 columns, which represent s, I, and r. We know this is true because we said the elements of the y vector are s, I, and r in that order. We can tell by the initial conditions as well. The 1,1 element is 10,000, which is our S0, the 1,2 element is 1, which is I0, and the 1,3 element is 0, which is R0. Once again, the first column represents S, the second represents I, and the third represents R. I'm going to parse these outputs within the epidemic function, remove the breakpoint, and fully run the code so we can see the plot. This is a really cool plot. The single infectious person immediately starts interacting with the susceptible people, so some susceptible people start getting sick. As the population gets more sick, you get more infected people, so it's not a coincidence that the S and I curves do the opposite thing early on. S falls because I rises. It looks like there's an equal number of susceptible and infected people around t = 3 days. Eventually, the total number of infected people starts tailing off just before 5 days, and then falls for the rest of the time period. This is because the number of recovered individuals starts going up. Just as S and I oppose each other early on, I and R mirror each other later on. Notice that the R curve only starts to rise after the I curve rises. We know this is the case because in order to be recovered, you first have to be infected, so naturally the R curve will lag the I curve by a little bit. If you find that your R curve immediately jumps up before the I curve, that's indicative of an error because you cannot be recovered before you get infected. If we go back to looking at the S curve, we see that everyone contracts the virus at some point in time because S eventually goes to 0. I eventually goes to 0 too, which means that everyone is eventually recovered. Thankfully, this is a pretty optimistic model. Now let's scrutinize some of the details of this problem. We said the initial conditions were S0 equals 10,000, I0 equals 1, and R equals 0. This means the city has a total of 10,001 people. In order to obtain the 3 first-order ODEs, we applied the so-called conservation of people. Conservation of people implies the total number of citizens is constant. Nobody leaves or enters the city, nobody dies, or nobody is born within the 40-day time span. Ideally, conservation of people should be evident in our plot. How can we check that? At any point in time, everyone is either susceptible, infected, or recovered. You can only be one of those 3 groups at a single point in time. It stands to reason that if we add the S, I, and R counts at any point in time, the sum should always be 10,001. Why 10,001? Because the initial conditions stipulate that there's a total of 10,001 people in the city. Let's check this. I made a variable called ptot, which is just the sum of each group, and then plotted it over time. We can see that the total number of people in the city is a constant 1.0001e4, or 10,001 people. If you zoom in, you might see some very slight oscillations on this line, but we can write that off as numerical error. If you make the absolute or relative ODE 45 tolerance tighter, the line will appear flatter. Now let me ask you some abstract questions. I'm going to go back to the PowerPoint to do so. Just to recap, we have our system of equations here. What is the product 1ty? In this case, 1t means a vector of 1's transposed. If we carry out the multiplication, you get s plus I plus r, which we already said is the number of total people in the city. Now what if we take the derivative of 1ty? 1t is a constant, so we can move it outside the derivative operator. The d dt of y is really just dy dt. By the way, whenever you see a column vector being multiplied by a row vector of 1's or vice versa, it just means you sum the contents of that vector. In this case, 1t dy dt is the sum of s dot, I dot, and r dot. If we sum this vector, we'll find that every term cancels out, so the sum is actually 0. This contextually means the change in the number of people in the city over time is 0. Over the time span, the status of each citizen changes, but everyone remains alive. For instance, I might be susceptible on day 2, but become infected on day 5, then fully recovered on day 12. This is a restatement of conservation of people, and it's also how you can check whether conservation of people holds true. This is not some astounding discovery that happens to be a mathematical artifact. Rather, it's a byproduct of the fact that we applied conservation of people to perform the population balances and wind up with these equations. This is just a neat little tidbit on how the underlying physics of the model manifests itself mathematically. I hope this blew your mind, because it sure did when I first solved this problem. Let's do one more thing. We know that ds dt equals negative ASI. Therefore, at t equals 0, ds dt should be negative a times s naught times I naught. You can actually change the time to anything you want. If you want to find ds dt at, say, t equals 15, you multiply the negative a by the s value at t equals 15 and the I value at t equals 15. T equals 0 happens to be very convenient because we know s and I at t equals 0. They're just the initial conditions. Let's go back to Matlab to find out what these values are. Let's see what ds dt is at t equals 0. If we pull up figure 1, the initial slope of the s-curve looks kind of flat, but if we zoom in a lot, we can actually see some sort of gradient. If you think back to numerical differentiation, we can estimate the value of ds dt using a forward, backward, or central difference. Since we're differentiating at t equals 0, we can only use the forward difference. Well, we have the t vector and we have the s vector, so let's compute the forward difference at t equals 0. Lo and behold, we get something very close to what the analytical derivative is. This tells us that our plot is most likely correct. If we wanted to make this numerical estimate more accurate, we could decrease the step size of our t vector. As the step size gets smaller, the numerical estimate of ds dt will eventually converge to the analytical value of ds dt. I hope this rings a bell. You can do the same thing for the I and R curves as well. This concludes the epidemic problem. To recap, we applied our own makeshift conservation law to formulate the system of differential equations governing the spread of an epidemic through a city. We then interpreted the results after numerically solving it with ODE 45 and did some decently rigorous and somewhat abstract math to confirm conservation of people holds true. We checked the ds dt curve at t equals 0 numerically to make sure that our plot has the right shape. Like population modeling, epidemic modeling is a constant work in progress. There are many models of various complexity in the world, such as the plentiful COVID modeling dashboards you've probably seen. In your homework, you'll get to explore an improved epidemic model. You can translate all of the concepts and techniques from this video to your homework, so be sure to re-watch this one if you get stuck. This is a really fascinating problem and is one of my favorites in this class, and I hope you think so too. See you next time.